do another one. Let's say this other one is that I want to figure out a reaction between SnCl2 and let's say K2Cr2O7 acidified, right? This is a reaction that I want to figure out what's going to happen. So what were the steps that I told you to take? The first step was step number one, that you identify the reactants. What are your reactants? And you treat ionic compounds as separate ions. Like in SnCl2, you have Sn2 plus and you have Cl minus 1. In K2Cr2O7 acidified, you have K plus 1, Cr2O7 2 minus, and there's H plus 1 as well. So these are my reactants. Is this clear?
Yes, sir.
I said the second step was that you write down all redox reactions involving these reactants, involving all of them, whether they're gaining electrons, whether they're losing electrons. I'm going to start with Sn2 plus, and let's open the data booklet and let's try and find Sn2 plus somewhere in these equations. So anything that happens to Sn2 plus, I'm going to write that down. So here's S, and here you can see Sn2 plus. So there's this equation over here, right next to my pointer where Sn2 plus. So I'm going to write each one of them. Uh, in reality, you would have a physical data booklet with you. So you wouldn't have to actually write these equations. So Sn2 plus 2 electrons Sn, and this equation is minus 0.14 volts. There's another equation involving Sn2 plus. It's this one. There's Sn4 plus, which is in equilibrium with, would gain 2 electrons to form Sn2 plus, or vice versa. And the value for this is it's positive 0.15 volts. So it's positive 0.15 volts. Then I had Cl. For Cl, there's one electrode which is over here. It's somewhere over here. It's Cl2 plus 2 electrons in equilibrium with 2 Cl minus 1 ions. And this value is 1 point plus 1.36 volts. Then what else did I have? I'm trying to predict this reaction, SnCl2 with K2, this K plus 1. So let me write down the K plus, there must be K somewhere. There's K plus 1 over here. So let me write that down, K plus 1 plus 1 electron in equilibrium with K, potassium. And this value is minus 2.92 volts. And then there was Cr2O7 2 minus, which is there's Cr2O7 2 minus over here. So let's write that down as well. Cr2O7 2 minus plus 14 H plus 1 plus 6 electrons in equilibrium with 2 Cr plus 3 plus 7 H2O. And the value is 1.33 volts. So coming back to our working, we are doing all the working. So what we have done is, let me move this slightly downwards. What I've done is that I had all these reactants. I had Sn2 plus, I had Cl minus 1, I had K plus 1, I had Cr2O7 2 minus, and I had H plus 1. So I had all these reactants, and I wrote down all the electrode reactions. I didn't know what was going to happen. So for example, if I picked Sn2 plus, I wrote down that Sn2 plus might gain 2 electrons to form Sn, or I wrote down this electrode as well where Sn2 plus is in equilibrium with Sn4 plus. It might lose electrons to form Sn4 plus. This reaction might go in the backward direction. So I'm not really sure what Sn2 plus wants to do. Similarly, I had Cl minus 1. So for Cl minus 1, I picked the electrode where there was Cl minus 1 present and it was losing electrons to form Cl2. So whether the reaction is going in the forward or the backward, I don't really care. Then there was K plus 1, so I came up with this electrode. I found this electrode. And for Cr2O7, I figured out this electrode. Now, the next rule is that the highest potential is the one that's going to gain electrons. So if you look at all these equations, the highest potential is being shown by which one? This is the one that has the highest E naught, right? It's 1.36 volts. So that means it has the greatest tendency out of all these possibilities, the greatest tendency for someone to gain electrons. Highest E naught is the one that gains electrons. So the greatest tendency for someone to gain electrons is going to be 1.36 volts. And this reaction would go in the forward direction. It would gain electrons. So based on the electrode potential values, I've chosen this one as the one that's going to gain electrons. But then I told you that the reactants must be present. So if I choose this reaction, then who's gaining electrons? It's Cl2 that's gaining electrons to form Cl minus 1. So in my reactants, I don't have Cl2. I mean, I have Cl minus 1, but I don't have Cl2. So I can't really use this equation. Okay, I can't really use this equation. I'm going to cut this equation out because although this has the highest tendency to gain electrons, but I don't have Cl2 in the first place. So how can Cl2 gain electrons? Sarah, is this clear? Aisha, is this clear?
Yes, sir.
Yeah, sir.
Aisha, then so I'm gonna put this aside. Okay, so I'm not going to use that equation. Then I'm going to again look for the highest potential equation. The highest potential equation is coming out to be this one. Out of the remaining equations, this is the highest potential. It's 1.33 volts. So which means if I choose this, then this is going to go in the forward direction. It has the highest potential. It likes to gain electrons. So Cr2O7 2 minus and 14H plus 1 would try to gain electrons. And in my reactants, I do have Cr2O7 and I also have H plus 1 ions. So there's nothing wrong with this equation. So I figured out that out of all these substances that I wrote down the reactants, it's Cr2O7 and K and H plus 1 that have the highest tendency to actually gain electrons. So I'm going to select this equation for the gain of electrons. So we can we've selected our equation for reduction. And then vice versa, we're going to figure out who's going to lose electrons. The one who loses electrons is the one that has the lowest potential. So the lowest potential right now is minus 2.92 volts. That is the one with the lowest E naught. Uh, so minus 2.92 volts, that means that it has the highest tendency to actually lose electrons, and it's going to go in the backward direction to lose electrons. But again, uh, if it is supposed to lose electrons, then it's potassium that's going to lose electrons. And in my reactants, I don't have potassium. I have potassium ions, but I don't have potassium. So I can't select this equation because I don't have potassium in the first place. So I'm going to cut this one out. I'm going to remove this. Because I don't have potassium. So how can it lose electrons? Now the lowest potential is the one, it's the first one, that's the lowest potential. So let's work on that. This is the lowest E naught. So it's going to lose electrons. And again, if it's going to lose electrons, uh, I can't pick this equation because then it's tin that's going to lose electron. I don't have tin. I have tin 2 plus, but I don't have tin. So again, I'm going to get rid of this. I'm going to reject this equation because it won't be able to lose electrons. So the remaining lowest potential equation is this last one. This is my final lowest E naught equation, because that's the only equation that's left. And if it was supposed to lose electrons, then 10 2 plus would be the one that would be losing electrons, and I do have 10 2 plus over here. So that means 10 2 plus out of all these 5 species, 10 2 plus is the one that has the highest tendency to actually lose electrons. And I'm going to circle this, and so I've figured out who's going to gain electrons. So in out of these 5, it's here 207 and 14H plus 1. They have the highest tendency to actually. I'm going to circle this over here. These two are the ones that like to gain electrons, and SN2 plus was the one that likes to lose electrons. So I figured out these two equations, and the next step is I need to write the overall equation. To write the overall equation, I need to balance the number of electrons that are lost and gained. So this equation over here, one of the equation is losing 2 electrons, the other one is gaining 6 electrons. So to make them equal, I'm going to multiply this by 3. So this 2 would become 6. So you multiply one of the equations or both of the equations so that the number of electrons that are lost and gained become equal. And then the last step is you add up the reactants and the products. You add up the reactants and the products. So you have the reactants in the first one is this one, 3SN2 plus. The reactant in the second one is Cr2O72 minus. Plus 14H plus 1, and the products. The products are in the first equation, the product is 3SN4 plus. And in the second one, the products are 2Cr3 plus 7H2O. So that's my overall equation. So that's my overall equation. And the other thing is I can write down the E naught cell for this. The E naught cell is the potential difference between the two equations that you selected, the lowest potential one and the highest potential. So it's highest E naught minus lowest E naught. So it's 1.33 volts minus the other one, which is 0.15 volts, which comes out to be 1.18 volts. Now, the higher this value is, the more feasible the reaction is. The more the potential difference, if the higher potential is really high, that means it really likes to gain electrons, and the lower potential is really low, that means it likes to really lose electrons. So the greater the difference between the two, the greater or more feasible the reaction is going to be. ठीक है सारा Aisha, is this clear?
Yes, sir.
Yes, sir.
So then you have so let's try another one, which is this one. We're going to do an example of homogeneous catalyst. So we're going to try and do an example of homogeneous catalyst. It's there's a specific reaction that needs to be remembered. That reaction is between Ki and K2S2 OA2 minus, or K2S2 O8. The reactants that you have K plus 1, you have I minus 1. Over here you have K plus 1, K is K plus 1, and S2O8 is 2 minus. So I haven't written K twice because there's K plus 1 already written. So your solution, your container has K plus 1 ions, it has I minus 1 ions, it has S2O8 2 minus. So these are the three reactants that you have. And you have to figure out what the reaction is going to be. So let's quickly write down all possible electrode reactions. K plus 1 is this one. It's minus 2.92 volts. For I2 in the data booklet, I minus 1, sorry. The equation is this one. That I minus 1 is in equilibrium with I2. And the value is 1 point. Let me check the value. It's for I. It's given at the bottom over here. This value is 0.54 plus 0.54 volts. ठीक है, remember don't forget to write this plus. And then S2O8, 2 minus. So there's this reaction for S2O8 2 minus, and the E naught is 2.01 volts. So three possible. You have three reactants, and these are the three possible electrode reactions. So which one has the highest potential? The highest potential is this one. It would like to, out of all the three, this one would be the one that would like to actually gain electrons. It has the highest tendency to actually gain electrons. So it's going to go in the forward direction. Now there's nothing wrong with it. Why? Because S2O8 2 minus would be gaining electrons. So we do have S2O8 2 minus as a reactant. So this reaction is perfectly all right. There's nothing wrong with it. I'm going to select this as my equation for the gain of electrons. So I'm going to select this as my equation for gain of electrons. Then I have to select the lowest potential one. The lowest potential one is this one, but I won't be selecting this. This is the lowest, although this is this is by far the lowest. This has the highest tendency to actually lose electrons. So it's going to go in the backward direction. But you can't select this equation. Why? Because potassium, you don't have potassium in your reactants. There is no potassium anywhere. So we're going to cancel this equation out. ठीक है Sara, Aisha, is this clear?
Yeah, sir.
So the remaining lowest E naught is this one. And it's going to lose electrons, and we do have I minus 1 in our reactants. So basically, at the end of the day, it's S2O8 2 minus that's gaining electrons, and I minus 1 that's losing electrons. And let me circle this. Sara, is this clear to you?
Yes, sir.
Acha, so we've figured out this. We can add the two equations up, and we can come up with an overall equation, which is going to be the electrons lost and the electrons that are being gained, they're equal. So we can simply add up the reactants and the products. So reactants and products. So the reactants are, in the first one, it's 2i minus 1. And in the second one, the reactant is S2A 2 minus. And the products are, in the first one, it's iodine that's being formed. And in the second one, the products that's being formed is 2SO4 2 minus. So I've figured out the overall reaction, and we can also calculate the E naught cell which is the potential difference between the oxidation and reduction equations. Higher potential minus lower potential, so it's 2.01 minus 0.54 volts. And this comes out to be 1.47. It comes out to be 1.47 volts. So that's my E naught cell, which is very, very feasible. So it's a very feasible reaction. Now, the reason we're discussing this particular reaction is because we have to study homogeneous catalyst. Uh, Now, if you look at this reaction is very feasible theoretically. It's a very feasible reaction. And why is it a feasible? Because it has high E naught cell. So it has a very high E naught cell, which means the substance that likes to gain electrons really, really likes to gain electrons because it has a very high potential. And the substance that likes to lose electrons, it has a low potential. So they're going to do their job. And theoretically, it has a high E naught cell. So that means the reaction is very feasible. But the reaction does not happen. This reaction has very high activation energy. It has very high activation energy and does not happen. Even though theoretically it's very feasible, in reality it does not happen. So what's the reason? Why is it having such a very high activation energy? The reason for that is that if you look at the two reactants, I minus 1 is reacting with S2O2 minus, you will notice that both of them are negatively charged. So these two in reality would never meet each other. Negative ions repel other negative ions. So even though reaction is feasible, but if in a solution there's S2O2 minus and there's I minus 1, they're never going to meet each other because they're both negative ions. So it does not happen. Why doesn't it happen? Because both reactants are negative ions. Are negative ions and they repel each other. So if they're never going to meet, how can they react? Is this clear, Sarah? Aisha, is this clear?
Yes, sir.
So the thing is, Sarah, is this clear to you?
Yes, sir.
So the thing is that these two are not going to react with each other. So I'm going to even though theoretically they were supposed to react with each other, this is the higher potential equation. So it's going to gain electrons. This is the lower potential equation. It's going to lose electrons. But the two equations are not going to react with each other. Okay, hopefully this is clear. Why are they not reacting? Because whatever, the overall reaction that you get, both ions are negatively charged and they're never going to meet. So this reaction looks good on paper, but it's not going to happen in a solution. So I'm going to place the two equations slightly further away from each other, and I'm going to assume that they are not reacting with each other. Now, homogeneous catalyst now plays a role. These two are not supposed to react with each other. Okay, we've clearly outlined what the reasons are. What you do is to make this reaction feasible in reality and to reduce activation energy, a catalyst is added, and that catalyst is either Fe3 plus or Fe2 plus. And in the data booklet, this is what Fe3 plus and Fe2 plus do, and this is the potential that Fe3 plus might gain electrons to form Fe2 plus, or vice versa. Fe2 plus might lose electrons to form Fe3 plus. The potential for this is 0.77 volts. So this has been added as a catalyst. and as a homogeneous catalyst specifically. So it's been added as a homogeneous catalyst. What it's going to do is that this equation, this iodine equation, is not reacting with the S2O8 equation, okay, because of these apparent reasons. This catalyst would help them react indirectly. What would happen is that the iodine equation we know is not going to react with the S2O8 equation. So instead, the iodine equation goes and starts reacting with the Fe3 plus catalyst. Fe3 plus is the higher potential. So it's the one that's going to gain electrons. And iodine comparatively, relatively, is the lower potential, so it's going to lose electrons. So it's going to go in the backward direction. So as soon as you add the Fe catalyst, uh, the iodine equation, let me correct this. So as soon as you add the Fe catalyst, the iodine equation, which was previously reacting with which wasn't reacting with S2O8, because both ions were negatively charged, so they were repelling each other. The iodine equation starts reacting with the iron equation, iron 2 plus or iron 3 plus equation. This is the higher potential, so it gains electrons. This is the lowest potential, it loses electrons. So they're going to react with each other. And we can come up with the overall equation overall reaction that's going to happen. I need to make the number of electrons equal, so I would multiply this by 2 because iodine was losing 2 electrons, so Fe must be gaining 2 electrons. And I can come up with an overall equation which is going to be add up the reactants. The reactant in the first one is 2i minus 1, and the reactant in the second one is 2Fe3 plus. And the products are in the first one, the product that's being formed is iodine, and in the second one, the product that's being formed is 2Fe2 plus. So I figured out this reaction that iodine, you added this iron catalyst, and iodine came and started reacting. This iodine equation came and started reacting with the iron catalyst. Is this clear, Sarah? Aisha, is this clear?
Yes, sir.
I said, then what's going to happen with this S2O8 equation? Even that is going to go and react with the iron catalyst. So even the S2O8 equation, it is going to react with the iron catalyst equation. And the S2O8 equation is the higher potential one, so it gains electrons. And the iron catalyst would be the one that would be losing electrons because it's the lower potential. This is the lower potential, this is the higher potential. So we can construct a reaction between these two. So what's basically happening is that this iodine equation wasn't reacting with the S2O8 equation because of the following reasons. When we added the catalyst, the iodine equation started reacting with the catalyst, and we figured out this is the reaction that's going to happen. And similarly, the S2O8 equation also started reacting with the iron catalyst. And S2O8 equation being the higher potential would be the one that would be gaining electrons, and the iron one would be the one that would be losing electrons. So we can come up with the overall reaction. The reactant is S2O8 2 minus, and the reactant over here is 2Fe2 plus, and the products are over here it's 2SO4 2 minus, and the product in the first in this iron, because it's going in the backward direction, it would be 2Fe3 plus. So you have these two reactions now happening. So the thing is, so I'm going to just quickly recap. The iodine equation and the S2O8 equation were supposed to react with each other. This was the lower potential, it would lose electrons. This is the higher potential, it would gain electrons. And you should have gotten this reaction. But I told you that both ions were negatively charged, so this reaction in reality never happened. So there was no point in reacting the two together because they're not going to react with each other. So you added these iron ions in the mixture, Fe3 plus or Fe2 plus, you added them, and this introduced a third reaction that was a possibility. And since iodine wasn't reacting with the S2O8 equation, the iodine equation started reacting with the Fe3 plus. The S2O8 equation also started reacting with this middle catalyst equation. In the first one, if the iodine reacted with this one, iodine was the lower potential, so it would lose electrons, and iron ion catalysts would be the ones that would gain electrons, and you would get this reaction. And if the S2O8 equation reacted with the iron ion catalyst, then iron ion catalyst was relatively the lower potential, so it would lose electrons, and the S2O8 equation would be the one that would gain electrons because it's the higher potential. And you got this reaction. Now, if you look at these two reactions together, you would notice that these two reactions can be considered step 1 and step 2. And basically, it's the same reaction broken down into 2 steps. I mean, if you look carefully, what's happening in this overall reaction, I minus 1 is getting converted into I2. The same is happening over here as well. It's I minus 1 getting converted into I2. What else is happening in this reaction over here? S2O8 2 minus is getting converted into 2SO4 2 minus. Over here as well, S2O8 2 minus is getting converted into SO4 2 minus. What's happening to the iron catalyst? If you look at the two steps together, you would notice that Fe3 plus in the first step changed into Fe2 plus, and in the next step, Fe2 plus changed back into Fe3 plus. So that indicates that there's no overall change that's happening to the catalyst. And you're getting both of your products, but in 2 steps. In the first step, I minus 1 gets converted into I2, so you get I2. And in the second step, S2O8 gets converted into SO4 2 minus, so S2O8 gets converted into SO4 2 minus, so you get the other product as well. So it's basically the same reaction broken down into 2 steps. And the ions, they don't undergo any change overall. You start off with iron 3 ions and you end up with iron 3 ions back again. So Fe3 plus or Fe2 plus ions, they remain unchanged. And act as homogeneous. Homogeneous catalyst means having the same state. Like they're also part of the solution, like the rest of the ions. So Fe3 plus and Fe2 plus remain completely unchanged and act as homogeneous catalyst. And this reaction is much faster. Why is it faster? Because now if you look carefully, in both the steps, step 1 and step 2, the ions are oppositely charged. I mean, I minus 1 is a negative ion, Fe3 plus is a positive ion. S2O 2 minus is a negative ion, the other one is a positive ion. So oppositely charged ions, they attract each other. So this second reason why the reaction is faster is both ions are oppositely charged and attract each other. So is this clear to everyone? Aisha,
Yes,
Sara,
sir.
okay. So we'll continue with this in tomorrow's class then, okay? Let me just
Okay.
complete this. So lesser activation energy. Said here. Okay then. Take care, Hafiz.